Have you ever looked up at the night sky, a velvet canvas sprinkled with countless stars, and felt a profound sense of wonder? It's a feeling that connects us across generations, across cultures. We ask the big questions. Where did all this come from? How did it all begin? The story of our universe is the grandest epic we know, and its first chapter is the most mysterious of all. We call it the Big Bang, but the story doesn't necessarily start there. It starts with a question that tickles the very edge of our understanding. What was happening before the beginning? It's a question that pushes science and philosophy into fascinating, uncharted territory. Imagine trying to describe what's north of the North Pole. The question itself doesn't quite make sense within our framework of direction. In a similar way, asking what came before the Big Bang is a puzzle for physicists. The concept of before, a marker of time, might not have even existed. The universe we know, with its unwavering forward march of moments, hadn't been born yet. Scientists explore this pre-cosmic realm with ideas that sound like science fiction. Some theories propose a multiverse. Other ideas suggest a cyclical universe, one that expands, collapses back on itself in a big crunch, and is then reborn in a new Big Bang, over and over again. So what was there before the Big Bang? The honest and thrilling answer is, we don't know for sure. There was only potential, a singularity. Let's set the cosmic clock to 0. At this moment, our universe ignites. This isn't an explosion in space like a firework bursting in the night sky. It is the explosion of space itself. Every point in the universe began expanding away from every other point simultaneously. Imagine a loaf of raisin bread dough rising in an oven. As the dough expands, every raisin moves away from every other raisin. Our universe is that loaf of bread. We, and every galaxy we can see, are the raisins, carried along on currents of expanding space. In the very first sliver of a second, the universe underwent a staggering growth spurt. We call this period inflation. The universe expanded faster than the speed of light. It ballooned from a size smaller than an atom to something larger than a grapefruit. This violent expansion smoothed out the cosmos. It ensured the universe would look roughly the same in all directions, what our telescopes observe today. After this inflationary burst, the universe became a scorching, dense soup of fundamental particles. It was hotter than the core of our sun, a chaotic inferno of quarks, electrons, other exotic particles, all zipping and colliding with incredible energy. There were no atoms, there were no stars, there were no galaxies, just a seething, opaque plasma of energy and matter, indistinguishable from one another. Think of it as a cosmic fog so thick and hot that light couldn't travel more than a few inches without being scattered. This primordial state didn't last long. As the universe expanded, it began to cool down. Just as steam condenses into water, cooling allowed ingredients to start combining. Quarks began to clump together, forming the first protons and neutrons. The universe was like a cosmic kitchen, slowly cooling so ingredients stopped flying apart and started forming the first stable structures. The grand cosmic firework was over, and the patient work of construction was about to begin. One of the most profound consequences of the Big Bang is that it didn't just create matter and energy, it created the very fabric of reality itself. Space and time were born in that initial moment. Albert Einstein's theory of general relativity taught us that space and time are not separate static concepts. Instead, they are woven together into a single, dynamic fabric called spacetime. This fabric is not just a passive backdrop for events, it can be stretched, warped, and bent by mass and energy. Think of spacetime as a giant stretched rubber sheet. A heavy object, like a bowling ball placed on the sheet, will create a dip or a curve. This curvature is what we experience as gravity. Now, imagine the Big Bang. It wasn't an object placed on the sheet, it was the sheet itself, unfurling and expanding from an infinitely dense point. The expansion of the universe is the ongoing stretching of this space-time fabric. The very room of the cosmos is getting bigger, and the clock of the cosmos started ticking at that very first moment, setting in motion the sequence of events we call history. This means that time itself has a history. In the fiery, dense conditions of the earliest universe, time would have behaved very differently than it does today. As you get closer to the singularity, the curvature of spacetime becomes extreme, and time slows down. At the singularity itself, time would effectively stop. This is why the question, what came before the Big Bang, is so tricky. It's like asking what is south of the South Pole. So when you look at distant galaxies, you are not just looking across vast distances of space, you are looking back in time. The farther we look, the further back in time we see, all the way to the faint residual glow of the Big Bang itself. Our telescopes are time machines, allowing us to witness the cosmic history that unfolded on the stage of space-time, a stage that was created in the very first act of the play. For the first few minutes after the Big Bang, the universe was basically a nuclear furnace. The temperatures were so high that protons and neutrons could fuse, forming the first atomic nuclei. This process is called Big Bang nucleosynthesis. The universe's recipe: for every 10 protons, which are hydrogen nuclei, it created about 1 nucleus of helium along with trace amounts of lithium. For hundreds of thousands of years, these nuclei floated in a sea of electrons. The universe was a hot, opaque fog, light trapped within it. Then about 380,000 years after the Big Bang, the universe reached a critical milestone. It cooled to about 3,000 degrees Celsius. Positively charged atomic nuclei captured negatively charged electrons, forming the first complete electrically neutral atoms, mostly hydrogen and helium. This event is called recombination. Suddenly, the cosmic fog lifted. Light was no longer scattered by free electrons and could travel unimpeded. The universe became transparent. That first light is still traveling through the universe today, and we can detect it. As space expanded over 13.8 billion years, this ancient light was stretched to longer, cooler wavelengths. It's no longer visible light, it exists in the microwave part of the spectrum. We call it the cosmic microwave background, or CMB. When we map the CMB, we're looking at a baby picture of the universe. Those first atoms of hydrogen and helium weren't spread perfectly evenly. Tiny fluctuations in the CMB made some regions slightly denser. Over hundreds of millions of years, gravity pulled those denser regions together. Clouds became denser and hotter. In their hearts, pressure and temperature ignited nuclear fusion. The first stars were born, lighting up the cosmic darkness. These stars forged heavier elements in their cores and, through their spectacular deaths, seeded the cosmos with ingredients for planets and for life. From a single point of unimaginable energy to a cosmos teeming with 1 trillion galaxies, the story of the Big Bang is our story. It's the story of how everything we see and everything we are came to be. The carbon in our bodies, the iron in our blood, the oxygen we breathe, all of it was forged in the hearts of stars that lived and died long ago. Stars that would not exist without the initial expansion that started it all 13.8 billion years ago. We are, in the most literal sense, stardust. We are the universe made conscious, capable of looking back and piecing together the story of its own origin. But the story is far from over. In fact, we've recently discovered some shocking plot twists. For decades, astronomers assumed the expansion must be slowing down. Observations of distant supernovae in the late 1990s revealed something astonishing. The expansion is accelerating. Something is pushing the universe apart, overpowering gravity. We call this mysterious force dark energy, and honestly, we have no idea what it is. It seems to make up nearly 70% of the universe, yet it remains a profound enigma. The stars and galaxies we can see make up only about 5%. Another 25% is called dark matter. We can't see it, we can't touch it, but we can detect its gravitational influence holding galaxies together. It's an invisible scaffold, the cosmic web, upon which the visible universe is built. 95% of our universe is dark matter and dark energy, unknown to our science. Our grand cosmic story is missing the vast majority of its main characters, and so we find ourselves back where we started, looking up at the sky with a sense of wonder. The Big Bang Theory is a triumphant achievement of human intellect, stitched together from mathematics and observation. Yet for every answer, a dozen deeper questions arise. What is dark energy? What is dark matter? Are we part of a multiverse? The edge of our knowledge is the frontier of discovery. The universe is under no obligation to make sense to us, and that is the most exciting part. The greatest chapters are still unwritten, waiting for the next generation of curious minds to explore.